Hello dear students, welcome to physics online class. So in previous video we discussed about the concept related to electrostatic potential in case of a hollow sphere and in case of a solid non-conducting sphere. So for these two, hollow sphere, hollow conducting sphere and hollow non-conducting sphere, and as well as a solid conducting sphere, for these three, so we are having the same formula, and that formula will get differ for that. So in case of a solid non-conducting sphere, so in case of that solid non-conducting sphere also we derived the expression for that electrostatic potential inside a solid non-conducting sphere. So now in today's class, so let me consider two sphere here. One sphere is enclosed in the other sphere, so these two spheres will get connected by one wire. Then what happens here? So charges are flow from that one sphere to other sphere. Then what about the potential of the second sphere? I need to find out. So for example, so I will consider the two sphere here. So for example, this is one sphere. This sphere I will name it as a sphere B, and this sphere having that radius small b, I will take it, and another sphere I will enclosed in the sphere B here. This sphere I will name it as a sphere A here. This sphere A is enclosed in the sphere B here. Where is the location of the sphere A here? Sphere A is located inside the sphere B, and sphere A having the radius A, and so there exists a certain kind of charges on the sphere A here. So for example, that sphere A having certain kind of charges here, and so I will make a connection between sphere B and sphere A by one wire here. So these two spheres are getting connected by one wire here. So now let me consider that. So what is the potential on the B here? So for example, so consider a sphere A of radius. What is the radius of the sphere A here? Of radius small a, of radius A, and it is enclosed in a sphere B, and it is enclosed in a sphere B of radius small b, I will consider here. Now let me find out that, so if that charges q amount will get distributed on the surface A, means what is the potential of that point A, I will consider here. So if charge q is on sphere B, charge q is on sphere A here. So on that sphere A, q amount of charge is present here. Then what about the potential here? So in case of that electrostatic potential due to a isolated point charge, electrostatic potential in case of a hollow sphere, so when the point of observation is on the surface of the sphere, what is the formula? Q by, what is the radius I consider here? Q by A here. So what is the potential value in case of that sphere A here? V is equal to 1 by 4 pi epsilon naught Q by A here. Shall I rearrange this equation in another manner? So Q is equal to what? So Q is equal to V into 4 pi epsilon naught into A. So shall I rearrange this equation here? Q is equal to V into 4 pi epsilon naught into A here. Now I will consider that. So these two spheres are getting connected by one wire, I said. So these two spheres are getting connected by one wire, means now let me find out that what is the potential at point B here. So look at here, charges are flowing from that A to B here. Why? Because between that sphere A and sphere B, I will connect by one wire here. It means that charges are flowing from that sphere A to sphere B. These charges are located on the surface of the sphere B here. Then potential at sphere B I will consider. So potential at sphere B, and V of A is potential at sphere A, I will take it here. So V of B is equal to 1 by 4 pi epsilon naught Q by B here. So look at here, what is the potential at that surface B here? So charges are flowing from that surface A to surface B here. So on the surface of that sphere B, charges are getting accumulated here. So look at here, wherever Q is there, so shall I fill that Q value as the V of A into 4 pi epsilon naught? So V of A into 4 pi epsilon naught into A here. So I will substitute that. So I will substitute equation 1 value in equation 2. So if I do like so, I will get that V of B is equal to what? 1 by 4 pi epsilon naught. So wherever Q is there, so look at here, V of A 4 pi epsilon naught into A divided by B here. So this term will get cancelled out here. So if it will get cancelled out, means V of B is equal to what? A by B into V of A. So potential at point B here. So potential at the surface B is equal to A by B into potential at surface A here. So where A indicates that, so radius of the sphere A here, and B indicates that radius of the sphere B here. So what is the potential at B here? So potential at the surface of B is V of B is equal to A by B into V of A here. So next I will consider that. So I will consider two hollow sphere here. These two hollow sphere having the common center. So if these two hollow sphere having the common center means, so now let me find out that what is the potential at the common center. So now my intention is to find out that potential at the common center. So in order to calculate the potential at common center, I will choose two hollow sphere. These two hollow sphere having the same center here, and charges distributed on these two hollow sphere. So I will take it as a Q1 and Q2, and these two hollow sphere having the same surface charge density. So let me find out that potential at common center. Potential at common. So just now we derived, so that is not a common center. So one sphere is enclosed in the another sphere. So these two spheres are connected one wire. So charges are flowing from that one sphere to other sphere. Then potential on the other sphere. So V of B is equal to A by B into V of A. Now I will consider that two hollow sphere, and these two hollow sphere having the common center. So potential at common center. So now I will find out that potential at the common center. So for that purpose, I will consider two sphere here. So this is one sphere and this is other sphere. For example, so this is common center for that sphere A as well as for sphere B here. So for example, sphere B having the radius capital R and sphere A having the radius small r here. So first let me consider that. Consider two sphere. Consider two sphere here. Two sphere A and B. These two sphere I will name it as a and B having radius here. Having radius. What is the radius of sphere A here? Having radius R and capital R, where capital R value is greater than the small r here. Small r. Let Q1 and Q2 be the, so let Q1 and Q2 be the charges on A and B having same surface charge density. So surface charge density of sphere A is equal to surface charge density of sphere B. So in generally, so surface charge density is sigma on the sphere A as well as surface charge density is sigma on that sphere B here, having same surface charge density, same surface charge density. Surface charge density. So now So what is the charges on that body A as well as on that body B here, Q1 and Q2. So now I will consider from that conservation of the charge, total charge I will consider. So let me consider. So from conservation of the charge, Q1 plus of Q2 is equal to capital Q. So total charge Q1 plus of Q2 is equal to Q amount here. So let me take this as equation 1 here. So total charge Q1 plus of Q2 is equal to Q here. So they mention that surface charge density is same. So surface charge density is same means, so for example, sigma of A is equal to what? Sigma of B here. So sigma of A means surface charge density on the sphere A and sigma of B means surface charge density on the sphere B here. So from the concept of surface charge density, in charge and field we learned that linear charge density, surface charge density and volume charge density. Surface charge density is nothing but what? So charge per unit area here. So charge is on the sphere Q1, area of the sphere 4 pi r square here. Similarly, charge on the sphere B is Q of 2 and this one is 4 pi r square here. Radius of the second sphere is capital R here. So 4 pi term will get cancelled out. Shall I write this equation as Q1 by Q2 is equal to R square by R square here. So look at here, I got that equation Q1 by Q2 is equal to, so R square by R square. Now I will equate these two equation 1 and equation 2. So from these two equation individually I will get that Q1 value and Q2 value. So let me find out that individually Q1 value and Q2 value. So look at here. So Q2 value, Q2 is equal to what? Q2 is equal to, shall I write this equation as Q1 into R square divided by R square here. So look at here. So from these equation 2 I will rearrange here. So Q2 is equal to Q1 into R square divided by R square here. Now, so I will substitute that Q2 value in equation 1. So I will substitute here, put equation 3 value. So equation 3 value in equation 1 here. So if I substitute these value, so I will get individually Q1 value and Q2 value here. So Q1 plus of Q2 is nothing but what? Q1 into R square divided by R square. Q1 into R square divided by R square here. It is equal to what? Q1 into R square divided by R square. It is equal to capital Q. So simplify this equation. Q1 into R square plus of Q1 into R square divided by R square. If we take to right side, so Q into R square here. So what's the equation? Q into R square. I will take that Q as a common factor here. R square plus of R square here. So it is equal to Q into R square. So finally Q1 value is how much? Q into R square divided by R square plus of R square. So look at here, individually I got that Q1 value. Similarly, so I will get that Q2 value is also, so Q into R square divided by R square plus of R square. So I got that Q1 value and Q2 value. So now I will find out that what is the potential at the common center. So potential at common center is, so potential at common center. So total potential, so shall I write this equation as V is equal to V1 plus of V2 here. So V is equal to V1 plus V2 means, so V is equal to, so 1 by 4 pi epsilon naught, I will take out that common here, Q1 by R plus of Q2 by R here. So I will name this as a equation 6 here. So I got that total potential at the center, common center. So Q1 by R plus of Q2 by R. I know Q1 value and Q2 value. Just I will fill that Q1 value and Q2 value in equation 6. Then I will get the potential at the common center here. So look at here. So V is equal to what? 1 by 4 pi epsilon naught Q1 by R. So plus of q2 by r. So I will substitute. So put equation 4 and 5 value. 4 and 5 value in equation 6. In equation 6 here. So we'll get that final answer here. V is equal to 1 by 4 pi epsilon naught. So look at here, wherever q1 is there, what's the value of q1 here? Q into r square divided by r square plus r square. So q into r square divided by r square plus of r square. So in denominator already a smaller one term is there, into r plus of q into r square divided by r square plus of r square. So in denominator, so one capital R term is there, so into r here. So look at here, so one r term value is getting cancelled out here. V is equal to 1 by 4 pi epsilon naught q into r divided by r square plus of r square plus of q into r divided by r square plus of r square here. So this is the required equation. So further if I simplify means, so q, shall I take it as a common here? So if I take that q as a common factor, so let me take that q as a common factor here. So if I take that, so q divided by 4 pi epsilon naught here. So q divided by 4 pi epsilon naught means r plus of r divided by, so r square plus of r square, this is also common factor, I need to take it here. So I will rearrange here. So 1 by 4 pi epsilon naught q into r plus of r divided by r square plus of r square. So this is the required equation for the common potential if these two spheres are at a common center here. What is the potential at the common center here? V is equal to 1 by 4 pi epsilon naught. So capital Q represents the total charge on the sphere A as well as on the sphere B. So r plus of r divided by r square plus of r square. So this is the required equation I need to consider. So in case of that concentric sphere, so let me find out that what is the potential at the sphere, at the first sphere. So potential between the first sphere and second sphere, potential on the second sphere, and potential at the outside the second sphere. So in these 4 points I need to find out the potential here. So first one, potential at the inner sphere, potential at the outside the inner sphere and inside the outer sphere. So potential on the second sphere and potential on the outside the first sphere as well as second sphere. So these are all the different cases I will take it here. So look at, so I will consider two concentric sphere. So in that concentric sphere, so I will find out that potential value at different region here. So in order to get that potential value at different region, so first I will choose that two hollow sphere here. So this one is sphere A, I will name, and another one is sphere B here. And so for example, sphere A having the radius A and that sphere B having the radius B here, small b. So now I will choose that. So I will choose that one point here, that is point R here. So this point of observation is present inside the first sphere. Where is the location of R here? So R is less than that of A. It means that, so where is the location of that point R here? So point R is present inside the first sphere. Inside the sphere A, inside the sphere A here, then potential value at that point 1 by 4 pi epsilon naught, V is equal to 1 by 4 pi epsilon naught q1 by A plus of q2 by B here. So what is the potential value here? V is equal to 1 by 4 pi epsilon naught q1 by A plus of q2 by B here. So second I will consider, so if r is equal to a. So if r is equal to a means where is the location of this point here? So point r is present on the surface of the first sphere here. So on the surface of sphere A, on the surface of sphere A. So in this position or in this situation as also I am having the formula V is equal to 1 by 4 pi epsilon naught Q1 by A plus of Q2 by B. So it means that so potential value is remains same at inside the first surface as well as on the surface of the first sphere here. So potential value will be remains same inside the first sphere as well as on the surface of the first sphere. So now let me choose that another position here. So for example, so this is the new position here. So this position is, so look at here, this position is outside the first sphere and inside the second sphere here. So if r is, so r value is greater than that of A and r value is less than that of B here. So look at here, where is the location of point r here? So r is greater than the A here. So it means that so position is outside the first sphere here. So position is outside the first sphere and inside the second sphere. So in this situation that formula becomes so 1 by 4 pi epsilon naught Q1 by R plus of Q2 by B here. What is the formula? Q1 by R plus of Q2 by B here. So this is third case. In fourth one, so if R is equal to B, so R is equal to B means what? So R is equal to B means so point of observation is on the surface of the second sphere here. So if it is so 1 by 4 pi epsilon naught Q1 by B plus of Q2 by B here. So what is the formula here? So if the point of observation is on the surface of the second sphere here, so what is the formula here? V is equal to 1 by 4 pi epsilon naught Q1 by B plus of Q2 by B here. Suppose if the point of observation is outside the outer sphere as well as outside the inner sphere here. So next I will consider if R is greater than A and R is greater than that of B. In these two situations means that point of observation is outside the inner sphere as well as outside the outer sphere. So in that situation V is equal to 1 by 4 pi epsilon naught Q1 by R plus of Q2 by R. So these are all the connecting formula in case of a two hollow sphere, and these two hollow sphere having the common center here. So in case of that common center, let me find out that potential inside the first sphere and potential on the surface of the first sphere, potential at the outside the first sphere and inside the second sphere, potential on the surface of the second sphere and as well as potential on the outside the outer sphere as well as outside the first sphere here. So in all these situations I need to use these formulas to get the potential value at particular points. So hope you are understanding these things. So now let me solve some numericals related to electrostatic potential here. So look at here. Okay, so look at that seventh question in our college material. Two parallel plates separated by a distance of 5 millimeters. So separation between the two plates, so that is 5 millimeters. So 5 into 10 to the power of minus 3 meter here, are kept at a potential difference of 50 volt. What is the potential difference between these two plates? So differ in the potential between these two plates is 50 volt here. And then they mention a particle of mass 10 to the power of minus 15 kg and charge 10 to the power of minus 11 coulomb enters with a velocity of So enters with a velocity of 10 to the power of 7 meter per second. So look at here. So this one is plate A and this one is plate B. Between these two plates, so they applied the potential difference value as a 50 volt, and the distance between these two plates is 5 millimeter, and one charge particle is there. That charge particle having the mass, they mention the mass of the charge particle, that is 10 to the power of minus 15 kg, and this charge particle is moving with a certain velocity. That velocity of the charge particle is 10 to the power of 7 meter per second. So in this situation, so they asked to calculate that acceleration of the particle will be. So I want to calculate that acceleration of the charge particle. So what is the connecting formula I have? So acceleration A is equal to what? E into Q divided by M. So in that first chapter we got this equation. So acceleration A is equal to E into Q divided by M means, so they didn't mention that electric field value, but they mentioned potential value and separation value. So I know that relation between electric field and potential. So in magnitude, so shall I take that E is equal to V by D here? So if I take like so, V by D, so here Q term is there, M. So acceleration A is equal to V into Q divided by D into M here. Potential value is how much? 50. Charge on the particle, so charge on the particle is 10 to the power of minus 11 coulomb. So 10 to the power of minus 11 coulomb here, and separation is 5 millimeter. So 10 to the power of minus 3 here, and mass is 10 to the power of minus 15 kg. So what will be the acceleration value here? 10. So 10 to the power of 1 into 10 to the power of minus 11. So 10 to the power of minus 10 here, minus 3 minus 15. So 10 to the power of minus 18 here. So 10 to the power of minus 10 plus of 18. So A is equal to 10 to the power of 8 meter per second square. What is the acceleration value here? 10 to the power of 8 meter per second square here. So look at next one. A cloud is at a potential of 8 into 10 to the power of 6 volt relative to the ground. So what is the potential of the cloud here? Cloud here. So potential of the cloud is 8 into 10 to the power of 6 volt with respect to ground. So potential between the 2 point here. So relative to the ground, a charge of 80 coulomb is transferred in lightning stroke between the cloud and the ground here. So during that during that training, that lightning is getting formed. That lightning consists of a charge, and that charge is transferring from that cloud to ground. So magnitude of the charge is 80 coulomb. So magnitude of the charge is 80 coulomb. Assume that potential of the cloud is to be remains constant, then energy dissipated. So which thing I need to calculate here? Energy here. So energy is nothing but a work I will consider here. So I have generalized formula. So V is equal to what? V is equal to W by Q. Work done is equal to V into Q here. Potential of the cloud is 8 into 10 to the power of 6 here. So charge is 80 coulomb. So 640 into 10 to the power of 6 joules. What is the answer here? 640 into 10 to the power of 6 joule, or I will rewrite here. So 6.4 into 10 to the power of 8 joules. What is the answer here? Energy dissipation from that cloud to the ground is 6.4 into 10 to the power of 8 joules of energy is transferring from that cloud to the ground here. So next one. Electric potential in volt varies with x according to the relation V is equal to 5 plus of 4x square. So they mention potential value in terms of equation. So 5 plus of 4x square here. The force experienced by a negative charge of 2 microcoulomb located. So what will be the force experienced by a charge? That charge having the magnitude 2 microcoulomb, and it is located at a distance of x value is 0.5 meter here. So 0.5 meter. So which thing I need to find out here? Force value here. So look at here, so field value they given, distance value they mention. So relation between field potential and distance. So what is the relation between that electric field and electrostatic potential? E is equal to minus of dV by dr or dV by d of x here. So first let me find out that electric field. After that I am having connecting formula between field and force here. So minus of d by dx of, what is the value of V here? 5 plus of 4x square. So differentiate this equation here. E is equal to minus of, differentiation of the number is 0, so 4x square becomes, so that is 8x here. So what is that differentiation of 4x square here? That is 8x. So they mention that value of the distance here, so 0.5 meter or 1 by 2. So 8 into 0.5. So that is value is minus of 4 Newton per Coulomb. What is the field value here? Minus 4 Newton per Coulomb. So they asked to determine the force experienced by the charge particle. So F is equal to what? So F is equal to E into Q. So I will use that equation here. So F is equal to E into Q here. So force value F is equal to E into Q. So electric field value is minus 4 Newton per Coulomb and magnitude of the charge is, so 2 into 10 to the power of minus 6 Coulomb here. So force is minus 8 Newton here. What is the force value here? So force is minus 8, sorry, 10 to the power of minus 6, 10 to the power of minus 6 Newton, minus of 8 into 10 to the power of minus 6 Newton here. Okay, so now look at that next question. Okay, so they mention the value in terms of graph. Variation of electric potential with distance d from a fixed point is as shown in the figure. The electric intensity at d is equal to 5 meter. So the given potential value and distance value in terms of graph. So from the graph I will take that potential value and distance value. Here they mention 0. Here it is. So let me draw the graph first. Here potential is 1, 3 and here potential is 5 and here distance 2. Here distance 4, here distance 5, here distance 6 here. So I want to calculate that electric intensity at a distance of 5 here. So they mention potential value and distance value. So electric field value E is equal to minus of dV by dr. So shall I take V2 minus of V1 divided by x2 minus of x1 here. So look at here, so V2 minus of V1 here. So potential value is, so V2 minus of V1, initial potential 0. So our V2 means finally the potential is reaches to 0. So minus of, what is the initial potential here? So that is 5 volt divided by x2 means 6 here. So x1 means 4. So 6 minus of 4 here. So look at here, E is equal to minus of 5 divided by 2 here, minus into minus plus. So 5 by 2. So 5 by 2 is nothing but a 2.5. So what is that electric field here? So electric field is 2.5 Newton per Coulomb or volt per meter here. What is that electric field? So in this position here, so electric field intensity at a distance of 5 meter is, so 5 meter means in between 6 and 4. So I will choose this as a potential, sorry, electric field at this point is, what's the value here? 2.5